Hello and welcome to the Superposition Guys podcast. My name is Yuval, and my guest today is Noel Goddard, CEO of Qunnect, a hardware company working to transform standard telecom networks into quantum secure communication networks. Noel and I spoke about first and second generation quantum secure networks, what one would need to do to create a secure link between Chicago and New York, the intersection of physics and telecom network engineering, and much more. We hope you enjoy this episode. Hello, Noel, and thank you for joining me today.
Well, it's a pleasure to be here.
So, who are you and what do you do?
My name is Noel Goddard. I am the CEO of Qunnect. We are a hardware company located in the Brooklyn Navy Yard that's building and innovating devices to transform standard telecom networks into quantum secure communications networks.
When people speak about secure quantum communications, they speak about many different things, starting from QKD to just purely quantum networks. I'm guessing you're focused more on the QKD, on the key distribution side. Is that correct?
Actually, we're the other side. I think that a useful way to think about the technologies right now for quantum communications is that there's a first generation of technologies which have actually been around for at least 10 years that are intended for hosting quantum key distribution protocols. And then there's a completely new set of hardware and protocols which are coming to light now, which have come out of sort of the research which people are doing towards the quantum internet. So when people start to talk about that, they're typically talking about distributed entanglement protocols. So in order to host those, you need completely new sets of equipment, and the protocols themselves are things which we've seen in laboratories, but not necessarily commercially yet. So Qunnect is on the latter side. We would consider that to be more like a second generation technology. So first generation quantum key distribution still communicates with single photons, the same way that we intend to communicate with single photons. But the difference is that the protocols which are currently used in QKD are point-to-point protocols, where they're depending on whatever protocol you're running in the background, like BB84. The user is sending a string of photons between sender and receiver. And depending on the protocol, randomizes the information, right? They do it in order to basically exchange and sift to get a key. In distributed entanglement networks, it's a little different because it's not intended to be point-to-point the same way. What you're doing is you are taking a pair of photons which were entangled and have some information on them and distributing them between sender and receiver. And in both cases, I think the major challenge in the field has been the fact that we would all like to do this over fiber, but fibers inherently have transmission losses. The longer you try to extend transmission with a single photon through a fiber, the more chance you have of losing it. So something in the kind of 50 to 70 kilometer range is usually the limit at which people think is useful for having a single fiber link that can carry a photon without significant loss. When you hit that distance, then you need to figure out how you're going to extend it. And in QKD, or the first generation technologies that we were talking about before, the way that people have been extending the distance is that they create a duplicate set of hardware at a node, which basically decodes the process, makes the information classical, then re-encodes the information into quantum, and then sends it again down another segment of fiber. Those relay nodes have commonly been called trusted nodes because they need to be highly secure in order to make sure that the process stays secure. But actually, they are vulnerable, which has been the reason that agencies such as the NSA in the US have come out against these types of technologies, because they believe that they can't truly be end-to-end secure to justify the cost of upgrading the hardware. In quantum networking, the protocol which allows you to extend the distance is something called entanglement swapping. And it allows you to basically project the entanglement of pairs of photons which have never seen each other onto a shared set. And that allows you to gain distance stepwise between the original sort of origins of your photon pairs. That process itself, because there's no measurement in the process, is theoretically secure. I think that nobody has really shown this in commercial sense yet, so I always hesitate to say something like unhackable or totally secure because we don't know how things will work with other types of side attacks and such that people can figure out. But basically, what you're doing is that as long as the information remains entangled, then and there's no measurement, then the information is secure. And therefore, I think that there's a great promise with this new type of protocol like entanglement swapping. But the problem is that the hardware needs to be invented. So Qunnect's mission in the past 2 years has really been bringing the hardware that supports these protocols to the market. And we're not quite there yet, but we've made some good progress.
In terms of bandwidth, this is still, at the moment, a low bandwidth technology, right? So when I spoke about QKD, I meant that your technology would be used to swap the keys or to set the keys, but not actually for the actual transmission of high-speed information. Is that correct?
So I think that the big question mark on everybody's sort of like forefront right now is whether, so you build it, what are you going to use it for? And QKD, it was very clear that the purpose is to create a key. The reason people talk about keys being the sort of first use case has everything to do with quantum communications is never going to win with bandwidth, but they will always win with security. So you need to be able to send something which is sensitive on the security front, but can afford to be sent slowly. Keys are a great example of that because after you exchange the key, then you can send whatever information after that. You can wait as long as you want for the secure key. And after you have the key, then you and I can exchange information with that secure key in the background. I think we all forget that digital communications had to go through a growth process, that it wasn't always a high bandwidth thing. So I think that one of the challenges that we've always had is in trying to explain the story of why you need to invent new communications protocols and innovate hardware to host them is that we've sort of all enjoyed the luxury of the fact that we can stream tremendous amounts of data on something like our cell phones now. But in the 1960s, nobody was thinking that was possible when they were sending the first messages between two computers. So I think that we just have to accept the fact that there will be first and second and 10th generation technologies that eventually start to improve bandwidth. But it's something that it's just hard to imagine today what all the use cases could possibly be. Key distribution, I think, is just something that is a nice first use case.
So let's walk through the technology. Let's assume that I'm in the Chicago area and I think you're in New York. So the distance is more than 50 kilometers. We want to have a secure link between us. We don't want that security to be regenerated. So we don't want to convert classically and then back to entangled photons. How does the network look right now, and what would it need to have with your products to allow us to establish this secure channel?
So basically, first off, the fiber which exists in the ground today is fine for transmitting the types of information that we're talking about, as long as you don't have things which essentially are measurement devices on the fiber. So they often call this optically transparent, but all they mean is that you don't have things like classical amplifiers or classical repeaters on those strands. So the first thing you need to do is you need to find some fiber between you and me, which is optically transparent. And then every 25 to 50 kilometers, let's say every 25, so we can sell you more instruments, but every 25 kilometers, you're going to need to have a rack of instrumentation. Let me just start off by saying that to do any type of entanglement swapping protocol, the key devices which you need an entanglement source to generate a pair. You need a quantum memory to hold one half of that pair while the other one goes to do something in the network. And you need a swapping device or a Bell state measurement device in a middling node between two sets of entanglement sources and memories. So basically, if you can imagine that every other node has entanglement sources in it and memories, and every other node between those nodes will have swapping station type hardware in it. At its most basic level, that's a Bell state measurement device. However, in order to make all of this work in a network, you need more than just the quantum devices, because everything has to be really tightly regulated. So one thing you need is a distributed clock. So every single node is going to have a clock, which again is able to correlate to each other. And they have to do so with a sub-nanosecond time resolution, which is more than what digital needs right now. Another thing that they need to do is that all of the devices in each one of these nodes, in order to be able to communicate with each other, need to also be using very precise wavelength references. So you're going to need a wavelength reference in every node that has an entanglement source, so that you know that it's going to work okay. And then finally, because we are sending photons between each other over fiber, we have to recognize the fact that the fibers themselves are subject to environmental stress, and they can change the photon that we're sending. So you need, on top of that, some type of real-time calibration tool, which allows you to test the fiber segments at a time of the day, like during rush hour, or during a time when it's frozen, or during a time when it's a heat wave, and to be able to compensate for small changes in the fiber, which are actually going to change the information, because we're trying to communicate with single photons, right? Every photon counts. So basically, again, there'll be a rack of equipment in every 25 kilometers or so. Every other one will have entanglement sources. And between them, there will always be a swapping station. Now, of course, there will also be some other swaps to make this a sort of hierarchical network that actually functions. But that's sort of what you can imagine. And the way that we think about the protocol is that entanglement sources, imagine you have two entanglement sources that are in nodes that are flanking a center node that has a swapping station. The entanglement sources are putting out pairs of photons. Half of those pairs are captured at the node in the memories, and the other two go to the swapping station. They're doing this continuously. Whenever you have a successful swapping event, the swapping station communicates back to the entanglement sources, or actually to the memories, to those nodes, and says, successful event, the photons which you have in your memories are now entangled. So each time you have a successful swap, you gain the distance between the two outer nodes that projected to the middling node. And you can do that across the entire network, or you can do it in layers, like hierarchical layers. We have a bunch of sort of primary entanglement swapping events, and then a secondary layer, which then swaps those. But you quickly come across the problem that you want to make sure that your memories can hold your photons long enough to do all of this. And that's something that's still, obviously being developed in the field.
You speak about quantum memory, but I don't think it's the same type of memory that I would have, say, in my computer, 16 gigabytes of RAM. It sounds more like a programmable delay line for photons. Would that be a fair statement?
So it's very fair to think of quantum memories as delay lines, because essentially what you're trying to do is to take a photon, not damage it in any way, and then release it in a way that preserves all of the information and quantum states that were associated with the photon before. So there are people who actually try to sort of emulate a quantum memory by putting in delay lines. Our quantum memory is different because we use a process called electromagnetically induced transparency, which uses a control laser to modulate the transparency of a collection of atoms, in our case rubidium, inside of a vapor cell. So you essentially open a window in the medium by making it transparent to send a photon in, and then when you turn it off, the control laser off, the photon is then basically transformed into a spin wave, which uses trillions of atoms to collectively store the information in the photon. The amount of time which you can actually store is defined by how long you can wait before you again use the control laser to basically take the spin wave and the information and reconstruct the photon. So we work at room temperature, which means that our atoms are moving at these incredible speeds within the vapor cell. And in fact, we work actually in a heated vapor cell, so it's an even worse case scenario. But basically, right now, the sort of best we've done in our laboratory is 800 microseconds of storage. It's a tremendous amount of time to be able to think about taking one photon, spreading all of the information in the spin wave across a whole collection of atoms and then be able to actually reconstitute it with something with high fidelity. So again, you hit on the most important part, which is the idea that memories are necessary for regulating timing in networks. There are repeater schemes which are out there right now that don't use memories, which again, everything is, when you start talking about entanglement sources, you're talking about things which are non-deterministic. So one of the challenges is you think you probably made a photon, but it's still going to come out probabilistically in terms of time. So it's really nice to have something in the network which turns something which is probabilistic into something which is deterministic.
It sounds like super complex technology with a lot of different parts. You need photon sources, you need to generate entanglement, you need swapping, you need the delay, you need synchronization, calibration. How close is it to reality in terms of installing a test network or something that demonstrates that this actually works?
So there have been some demonstrations of entanglement swapping in academic laboratories. I think probably the most well known is a demonstration that recently happened in Delft. TU Delft in the Netherlands is definitely probably the most advanced quantum networking group in the world right now. They've done a number of interesting demonstrations and development of technology there to support various protocols, but the ones that they're doing right now to support entanglement swapping basically are using nitrogen vacancy centers and diamonds as their memories. This all has to be cooled to a few millikelvin in order to be able to function. So you need an entire laboratory of infrastructure around the devices which you want to use. But they have actually been able to demonstrate that they could do entanglement swapping between memories that are, again, supported by all of this other types of infrastructure over fiber. So what Qunnect is hoping to do, of course, is to show the commercial version of that using our devices. Again, all of our devices operate at room temperature at this point, so there will be different challenges in trying to put these online. Our goal as a company is that we just raised our first sort of large funding round, which was to support actually us building out a networking testbed that we can connect our instruments to so that we can learn how to do this best over real fiber. Because we happen to be located in Brooklyn, there's quite a bit of challenges because the fibers which are around here are obviously pretty noisy since we're in a very urban area. But that's good because then we'll learn how to deal with that in our networking protocols. I think we're probably 2 years out from really being able to do what I would call a real repeater protocol. But entanglement swapping, which is one half of the repeater, basically is something that's a real goal of ours over the coming year.
In terms of the composition of the company, I'm sure there are lots of physicists and people who have to deal with control electronics. To what extent do you need communication experts or people who are familiar with how telco infrastructures actually work?
It's a great question. We think about it a lot because now that we actually have the opportunity to expand, we're trying to figure out what the right answer is. We started off being largely physicists and engineers because we needed to basically design instrumentation. And the instrumentation was the first in its class in many ways. So the challenges were very hardware specific. Now that we want to try to connect things, we're starting to branch over into the network world. And I think we all understand that we would like for these things to run on the same fiber network that exists today across the country. There's no way to know how that works without including network engineers as part of the design process as we keep going forward. I think it's just a natural transition for a company that first we built the devices, now we need to plug them into something. And the plugging them into something brings that. I think the other piece, which obviously would be something that's very useful for the network engineering side of this, is to think about the control layer. At some point, if our devices are working well, there should be a software overlay, which is controlling all of the different nodes. And that's definitely something which starts to enter the network engineering world.
So, in a commercial sense, a Verizon one day would say, I can offer you special pricing for a super secure link between two endpoints. Do you see that as a federal customer? Do you see that as banking? Are there particular applications that are stand out as being more attractive?
Also a great question. I think that we all like to think of this as a few layers. So if you're talking about exchanging exceptionally secure but slow information, such as keys, that's extremely useful for different types of financial transactions, critical infrastructure transactions, defense transactions. There's a whole class of problems which that fits. But something that we think about a lot at Qunnect is how do you really take something from being just a communications network and turn it into an analogous internet? So the internet that we have today, the digital internet, connects all sorts of devices, computers, IoT, etc., right, over this hybrid structure which allows everything to be a mesh of connectivity. If we'd like to do the same thing for quantum, we need to think about how are we going to interface a quantum computer with a quantum communications network? How are we going to use quantum networks today in order to actually build sensor arrays so you can have quantum sensor arrays? Those types of things are exciting problems to think might be, again, on the horizon whenever these networks are a little bit more commercial and widespread. We at Qunnect also are thinking a lot about the fact that the types of qubits which you send over these networks are going to be important to sort of standardize. Right now, there are a number of different types of qubits that different groups use. There's a large number of wavelengths that different groups use. This is all because right now quantum has a lot of ways to work, but it's always very specific to the material which hosts the quantum effects. In our case, we use rubidium vapor, so that's very classic material for a lot of physics. So a lot of the wavelengths that we use are defined by that. That means that the communications wavelengths would be defined according to that, as opposed to somebody else who's using a different physical system like rare earths or something, and they would be using a different type of wavelength or different wavelength. If you're going to do that, then you need to have frequency converters, or you need to decide that there's a standard that everybody plays at. So I think that we have to evolve to a point that people can actually start talking about standards in the industry. That's not close, right? That is some distance away. But those telco providers like a Verizon, which you were mentioning earlier, they're watching and they're eagerly trying to learn so that they can prepare and understand what they may or may not need to do in order to host quantum information in the future. We use polarization qubits at Qunnect, which are traditionally thought of as more the computational qubit, not a communications qubit. We do that for a number of reasons. Our quantum memory natively stores them, which is perhaps the most important part of it. But polarization is something which also has a tendency to be something you get for free out of a lot of entanglement type processes. So we're right now building all of this equipment to basically show that polarization qubits can be used over networks, which I think is not something that people were really believing could be true, but they also are a very native match to quantum computers and quantum sensors, so that we can start thinking about the next layer problem, which is how do we connect the devices over this quantum communications network so you're not just sending keys.
As we get closer to the end of our conversation today, I wanted to shift away from the technology to ask two other questions. You mentioned that a lot of the advancements were actually international. You mentioned TU Delft. I read someplace that there was a secure video call between China and Austria. Do you worry that there are going to be export restrictions on your kind of technology?
Oh, there already are. I think that this is, the world is changing. I think that's just part of the real story. In America, the ITAR restrictions already apply to quantum encryption technologies. Qunnect doesn't build encryption technologies. We build all of the stuff that hosts quantum information. So you could think of us much more like the infrastructure that hosts quantum information as opposed to the end devices who do the encryption. Right now, you would not be able to export anything from the US that was a quantum encryption device. We hope, and I think this is just philosophically how we feel as a company, we would very much hope that the quantum internet is something that develops in Europe, in the US, in other countries independently and can eventually be connected the same way as the digital internet. But I think its special use cases, which go back towards that defense use case, are just part of the realities of where we are as a nation and a world. We understand that cybercrime is basically the crime of our lifetimes, right? And it's only going to get worse whenever quantum computers come online. So we'd be naive not to say that, of course, we understand that there are going to be restrictions at some point on some things. But for right now, I think that everybody's benefiting from it being a little bit more open technology so that we can all find the best solution globally.
I think you are a physicist by training, and now you're running this exciting technology company. If you could have dinner with someone in the quantum space, dead or alive, who would that person be?
And it's interesting. So my training is actually in biophysics. So I wasn't trained in AMO physics, which is primarily what we do here. Um, I had started off working in a photonics lab in graduate school and building instruments and doing those types of measurements. And then I saw this opportunity to do a sort of hybrid degree program. And when I went into biophysics, I spent quite a bit of time in the front end of biophysics, also building instruments to measure hard things. So most of the sort of heroes in my world, when you would ask this question on the front end, would have been people who were largely in the biophysics space. But there's something quite exciting that just happened in quantum communication science, and that's the Nobel Prize. So just a few weeks ago, the announcement of the winners of the Nobel Prize in Physics, of course, got it for showing entanglement technologies. I've been rather blessed to have had some light introductions to those teams, but it would be actually really fun to sit down and to have dinner with all three of them and to see how they believe that how special it is that their very basic research science is now something which people are talking about as commercial reality.
Excellent. So, how can people get in touch with you to learn more about your work?
So we just launched a new website, which we're rather proud of, which does show a number of interesting videos and animations. There's an animation on how a repeater network would work using our devices, but it's a great place to get started. We also have good intentions of making animations about all of our different devices. So if you go on to YouTube, you will see our quantum memory animation there. And as we continue to roll out products, we'll have more. We thought this was a great way to educate people on how these devices work. As well intentioned as white papers are, I think they don't necessarily get as much reading as we always hope. Whereas an animation is something that everybody can sort of appreciate, that visual learning is how we do things now. So that's a great place to start in terms of if you happen to be in the New York area and you'd like to come by for a lab tour, etc. We've been doing more of those recently. So that's another thing that you can always drop us a note and ask. So we have a general email line called contact@qcon.com.
Noel, thank you so much for joining me today.
Really a pleasure to be here. Thank you for the invitation.